we last time we finished actually the reinforcement learning, and then we will start to discuss the connections to physics and to science. So let me just give you an introduction how you might draw the connection between neural networks, artificial neural networks, and physics. So as you can see here, at least initially, when you think of an artificial neuron, you think of it maybe as something that can be off or on, especially if you have the sigmoid nonlinear activation function. And likewise, a real neuron could be silent, or it could produce electrical impulses. And so you can easily make a connection between this and a bit, which can be 0 or 1. And if you want to look for a bit in physics, you would take a spin 1/2 that can be up or down. And so neural networks have a strong connection to the physics of spin systems. And indeed, if you let them have stochastic transitions and you write down cost functions in terms of energy functionals, then you can make this connection mathematically precise. And there have been many different ways of making this connection. One particular I mentioned here on the slide was started by Mr. Hopfield in the beginning of the 80s. But this is not what we will discuss. We will not discuss so-called Hopfield models. Instead, what we will discuss is called a Boltzmann machine. And as I go along, I will explain to you what a Boltzmann machine really is. But first, I want to explain to you what is the goal of a Boltzmann machine. And that's a rather general goal in machine learning, namely to model probability distributions. Now, of course, if I give you a probability distribution like a Gaussian distribution, you could try to, say, construct a neural network that outputs in its output neurons the shape of this distribution, namely a Gaussian, for example. But that's not what we are talking about. We're talking about a situation where you don't want to represent the distribution function, but you want to produce samples according to a distribution function. And you don't want to produce samples according to a distribution function that is known to you, like analytically, but maybe you want to produce samples according to a distribution function that you only have observed empirically. So what could this mean? In practice, it could mean that I give you many different pictures, and you want to be able eventually, by having looked at all these pictures, to produce pictures that are sort of similar to the pictures that you have seen before. So that will be the goal of what we say. So in one sentence, to use a neural network of some type to generate previously unseen examples, but according to a probability distribution that you have sampled before in terms of training data. We already mentioned one version of this when we had a look at recurrent neural networks, LSTM networks, and we had this case where you would train it to predict the probabilities of the next character in a large text, and then you can use these probabilities to actually generate the next character in the text, and in this way you can generate a whole text. So in a sense, then you are generating a text according to a probability distribution, namely of characters, that you have trained before. And the nice thing about neural networks being used to model probability distributions is that there we will find a very close connection to statistical physics. So I don't know, maybe some of you have heard already statistical physics lectures, maybe some of you will still hear statistical physics lectures, so either it's a reminder or it's maybe even an introduction. And so I want to start really basic with statistical physics, essentially. So this slide is not at all connected to machine learning. Imagine you have a crystal lattice, and each atom has a spin. The spin can point down or up. But now these spins are interacting. You could think because of the magnetic dipole-dipole interaction, but that's actually not very important. There are other interactions like Coulomb interaction and exchange interaction that are important. So anyway, they are interacting. And so to each such spin configuration, to each such picture, you can assign an energy, the energy of this particular configuration. And if the interaction between the spins in this example is such that they want to align parallel, they want to point parallel like in a ferromagnet, then the energy of this configuration will be low, but the energy of that configuration, where the spins are more or less random, will be high. And so statistical physics tells us that in thermal equilibrium at a given temperature, the low energy configurations will be more probable and the high energy configurations will be less likely. Indeed, statistical physics does not only make such a qualitative statement, but it tells us exactly how the probability depends on the energy, and it tells us that the probability is essentially an exponential, where in the exponent I have minus the energy divided by kBt. kBt is the thermal energy. So this means in particular high energies are less likely because there's a minus sign in the exponent. Plus it also means that if I have lower temperatures, then this effect will get even stronger because low temperatures mean for a given value of the energy that this exponent, the magnitude of the exponent gets larger, and so I get even more suppression. So at low temperatures, the tendency towards having low energies is stronger. So this is the exponential Boltzmann factor. And then, of course, if this is supposed to be a probability distribution over states S, so each S corresponds to a full configuration. If this is supposed to be a probability distribution over such states S, then it has to be normalized. So this is the purpose of this prefactor 1 over the so-called partition function Z. Partition function Z is nothing but the sum over all Boltzmann factors. So then you see that this is a normalized probability distribution. You can just check it, you sum over all S, and you will find that then you have the partition function in the denominator, but also in the numerator, and it will cancel. So you get 1. Okay, so this is nice. In principle, this solves all of equilibrium physics. I give you the temperature. I also tell you how the energy depends on the pattern of spins, for example. And then you know the probability of each of these configurations. And for example, you could go ahead and calculate the average energy. You would just take the probabilities that we introduced and multiply them with the energy, sum over all configurations. That would give you the average energy. And you can get any other quantity you're interested in. You can also get what's the average spin. You just take the spin, take it as a variable plus or minus 1, multiply by this probability, sum over all configurations, you get the average spin. So you can get really anything. So then what's the problem? You might think that solves all of equilibrium statistical physics. Why are people still working on it? And the reason is that, of course, there are many, many such configurations, because each spin has 2 possibilities. So the total number of configurations is 2 to the power of the number of spins. And in a real macroscopic material, there will be a macroscopic number of spins, and now you raise 2 to the power of that number. So you have, as we say, exponentially many states, and to evaluate, even just to evaluate such a partition function is completely impossible. You cannot sum over these exponentially many states. And so that's a problem. And to solve that problem, people have introduced approximation methods. And these approximation methods will also be important for what we are going to do in machine learning. And the most famous and also simple approximation method is the so-called Monte Carlo approach. So the idea here is the following, before I go into the details. You try to start from some spin configuration. You start flipping spins, but according to certain rules. And you try to set up the rules such that eventually you will visit each spin configuration with a probability that is given by the Boltzmann distribution. If that is true, then in order to calculate any average you are interested in, you can just average over all the configurations that you visit during this dynamics, and that will give you the correct average. And it's stochastic in the sense that we will invent stochastic transition rules. And of course, we cannot expect that we will really sample all configurations because there are exponentially many of them. But it turns out for reasonable observables like the spin or even the product of two neighboring spins or any such observable or the energy, you can get away with sampling only a tiny fraction of all possible configurations. It still works. There's of course statistical fluctuations, so there will be a statistical error to your result, and it will get better the longer you sample. But in principle, you can do it like this. So this is the Monte Carlo approach, and of course it's called Monte Carlo because randomness is involved. So how does it really work? So one way to visualize it is to say, let me put each different spin configuration in such a little circle so that each circle represents a different state. So each of these circles represents a different state. That's a nice representation because now if I switch from one configuration to the other, it looks a little bit as if I'm jumping from one state to the other. So it's like jumping around in a landscape of different states. The states we denote by S. And then there will be transitions from one state to the other. So there will be, and these transitions are stochastic. So there will be a probability to go from state S to state S prime in a time step, and another probability to go from state S prime to S, so to speak, to go into the opposite direction. And for each of these arrows, there will be such probabilities. At the moment, I don't tell you yet how these probabilities are constructed. You could invent them on your own, and then just see what happens in such a game. So the game will now be the following. We start with one configuration, so I place my yellow dot at this particular configuration to indicate I'm here. I have this spin configuration. And then, according to these probabilities that are listed here at these arrows, I will make one of these transitions. So I go to one of these configurations that are connected. And again, I can, at this moment, I can still invent the rules. Here I only display 4 configurations to which I could jump. But this is a little bit arbitrary. In reality, I can jump to many more configurations. Maybe I can jump to an arbitrary other configuration. And we will say a little bit more about this later. But that's the game. So jumping around in configuration space. Okay. So this is what could happen. I jump to this particular side. And then I jump to that particular side. And maybe then there. And so I would go on and on and on, and I would, for example, for each configuration, I would record the energy, and then if I have a long time trace of 10,000 steps, I have 10,000 different energy values, and I could take the average of this, and hopefully this tells me something. But at the moment, this is still just a stochastic game. There's no guarantee that I get, for example, the Boltzmann distribution in this way. So one way to understand what's going on, to understand it a little bit better, is to imagine that instead of following one particular random walker, I have an ensemble of those. So as if I play my game many, many times in parallel. Because now I can basically follow what happens to this ensemble. Some of these points will go there, some of these points will go there, and then I can determine what happens step by step by step. And if there are really many points, I can keep track of the fraction of these points that are at any given time, say in this configuration or in that configuration or in that configuration. So I'm thinking of a point cloud that slowly spreads across my configuration space. And if I go to the limit of infinitely many points, I really can interpret this density of the point cloud like a probability distribution. Namely, it's the probability distribution if I pick a random one of these points, in which state will I end up? Okay. So you think in terms of this point cloud that slowly diffuses throughout configuration space. And now let me call this density of the point cloud, or the probability distribution P of S. Let me call this P of S. So P of S is still normalized to 1. It represents the probability, if I pick an arbitrary point, that I will find it in state S at this given time. Yes, there's a question. Yes, yes. There's also, in principle, a possibility to remain in the same state. That would be a transition where S prime and S are actually equal. Exactly, yes. Okay, and now we imagine this P of S as it slowly spreads, and we want to find what is the evolution of P of S, of this point cloud density. And so that's actually not too difficult to construct. So if I have P of S at a given time step and I want to know how it changes during one time step, then I can apply the following logic. I can say this state S, it will lose some particles and it will gain some particles. It will gain particles that jump from another state, let's say S prime, onto this particular state S. Then there's a net gain. But it will also lose some particles, namely those particles that already were in S, but now went out of S and end up in some other state S prime. Yeah? And in order to find out the total change of the number of particles in this state, I just have to balance these two fluxes, so the influx and the outflux. And so this is what is done here. So for example, look at this term. It describes the total influx. I take a sum over all possible neighboring configurations S prime, like this one, for example, or that one, and so on. I take how many particles are in this neighboring configuration, P of S prime, and I multiply that by the transition probability to go from S prime to S. That contributes to the influx. Of course, if there is nothing sitting in S prime, then this P of S prime will be 0 and it will not contribute to the influx, even if the transition probability is not 0. On the other hand, if there are some particles in S prime, but the transition probability is 0, I also will not get any contribution. Okay. So this is what happens here. This is the total influx. And then I also have the outflux, but that's equally easy. So I just take the number of particles that are sitting on state S, P of S. Or when I say number of particles, I should be more precise. I should say it's the fraction of all particles that sit on S. It's normalized to 1 in total. I take this P of S, I multiply by the transition probability to go from S to another site S prime. And that's, so to speak, an outward transition. That's something that I lose. Because I lose it, it enters with a minus sign. Okay, so this is really the time evolution equation. It describes really what happens. Sometimes the P of S decreases, sometimes it increases, and in general it has a tendency to distribute itself over configuration space. Okay, you find the same kind of equation in many contexts in physics. For example, if you have a gas of particles and you look at how they scatter and collide, and you want to look at the momentum distribution, you can write down a similar equation. There will be scattering events that bring a particle to a certain momentum, and also other scattering events that take it out of this momentum. And then you write down such an equation, which in this context is called a kinetic equation. And in the end, as an equilibrium state, you would find, for example, the Maxwell-Boltzmann distribution. Okay. So the claim is if you really wait long enough, if you have a large but still finite configuration space, and you really wait long enough, then this point cloud will distribute itself over all the states, and it will settle into something that is like a steady state. So there will still be these processes going on, particles jumping from one state to the other, but there will be no net change anymore, at least on average. So maybe there are 10 plus minus some number particles on one of the states, and this will remain fixed. So it really goes to an equilibrium state. And one can prove this, but I won't prove it now. Yeah. Okay, so it goes to a steady state where the P of S doesn't change anymore in time. Now, there's a very particular property that these transition probabilities can have, which makes it much easier for us to actually calculate the steady state. And this property goes under the name of detailed balance. So let me explain to you what detailed balance means. Again, this is a term from physics and is very important. Yeah? Suppose there exists a distribution P of S such that for any pair of states S and S prime, the ratio of transition probabilities between S and S prime equals the ratio of P of S versus P of S prime. That's a very special condition. It's very special. You can see this immediately because there are many more transition probabilities, because in principle for any pair of states there can be a transition probability, than there are P of S probabilities, because only for every state S I have a P of S. Yeah? So in principle I have a lot of freedom to choose these transition probabilities, and if these conditions are fulfilled, then that's a very special choice. Okay? But let's assume that this is fulfilled. Then it turns out if this is fulfilled for any pair SS prime, then P of S is the long-time distribution. How do we know that? Well, that is really easy to show. We just remember this particular equality, and now we go to this equation, and it just turns out if this equality is true, then this term equals that term, so the in and the out flux exactly cancel each other. Even just for a particular transition between S and S prime. I mean, if we are in the steady state, it must always be true that the overall change in one time step must be 0. That's the definition of the steady state. But this could also come about in a more complicated way, where the individual terms in the sum are not yet 0, but if I sum over all S prime, I finally get 0. But if I have detailed balance, each individual term in the sum that belongs to an individual pair of S and S prime is already 0. Yeah? So this is a very particular situation. And so if this is fulfilled, then P of S is automatically the limiting distribution, yeah? Because nothing changes anymore, so we just prove it. Okay, fine. So that's a peculiar condition. Now, this P of S could still be anything. But of course, we would like to have a situation where this P of S is the Boltzmann distribution. So now we will turn this equation around in a way. We will say, let us assume that P of S is the Boltzmann distribution for a given energy, and with a given, for a given temperature, excuse me, and with a given distribution of energies, E of S. And then this equation tells me how I should arrange my transition probabilities in order to arrive at the Boltzmann distribution. So instead of saying, let me start with transition probabilities and let me look where I end up, I say, I want to end up in the Boltzmann distribution. Let me use this equation to fix my transition probabilities. What is fixed really is rather the ratio that is shown here, not the individual probabilities. Okay. And so that's what I describe here. That's what people use to do Monte Carlo to get the equilibrium Boltzmann distribution. They just say, I know the right-hand side. I know the P of S. It should be the Boltzmann distribution. So let me just calculate this, and this is what the ratio gives you. If you have these Boltzmann factors that are exponential and you take the ratio, then you just get e to the, and then the difference of the energies of these two states. And then let me demand that my transition probabilities fulfill this relation. So we can take a moment to understand physically what goes on here. Let me assume that S is the S is, for example, the higher energy state. Let's say S is the higher energy state. Then E of S is larger than E of S prime. So the exponent is negative. So this number is less than 1, which means that likelihood to go from S prime to S should be less than the likelihood to go from S to S prime. So that means it's less likely to end up in S than it is to end up in S prime. And that is what should happen if S has the higher energy, because if it has the higher energy, it should end up with a lower probability, and this is exactly what these transition probabilities will make true. Yeah? So it's exactly the kind of transition rates that you would think are needed to make, in this case, P of S smaller than P of S prime, because E of S is larger than E of S prime. Okay, so now the only task is to construct transition probabilities that fulfill this ratio. And in principle, there are many different choices, because there are two quantities, S prime to S and S to S prime, so there are two transition probabilities, and there's only one equation, so I have a choice. But here's an example. So it's called the Metropolis Algorithm, after the guy who invented it. And it works like this. You just pick a random spin. You imagine you do a spin flip. Since you flip the spin, this will also change the energy of the system. It may go up or down, depending on which directions the neighboring spins are. And then the rule is the following. Do the spin flip. If it lowers the energy, then you always do this spin flip. But if this spin flip were to increase the energy, you don't always do this flip. Instead, you do something probabilistically. You flip the spin only with a probability that's given by this Boltzmann type factor, namely e to the minus delta E over kt, where delta E is the increase in energy. So if the energy decreases, always do the flip. If the energy increases, only do it with this probability. And then if you think about it, if you take the ratio of the transitions from this configuration to the new and back again from the new one to the old one, so if you take this ratio, then you get exactly this factor, because one of the two transition probabilities is 1 and the other is this factor. And then if you think about it, it is exactly what you need here, because there you see the difference between the energies. Yeah? So this is one way to construct such transition probabilities. And it's very simple to implement. You have a large lattice with spins. You pick a random spin. You imagine what happens when it flips. You calculate what this means for the energy. If it lowers the energy, you do the flip. If it increases the energy, you do the flip only with this probability. So that's it. And then there are many more advanced techniques, because here you flip only one spin, but then it takes a long time until you really have flipped all the spins. So there are more advanced techniques. However, all these techniques are constructed such that they fulfill this condition and that they will therefore end up in the Boltzmann distribution. Okay, so that's a nice, simple way to numerically generate a set of configurations that would end up in this Boltzmann distribution. And then you could do it like here, start out in one configuration and then follow such a cloud of configurations as it spreads. But you don't actually need to do it like this. You can now go back and only pick a single point, so only follow a single configuration as it is changed. And if you now do averages over sufficiently long times of any observable, it will be effectively the same as doing a Boltzmann average. Okay. So are there questions about this one? It's a very powerful and well-known technique. Okay. If you are interested, certainly you can Google on the internet and you find many different Monte Carlo simulations, for example, for the Ising model, which is this model of the spins. Okay. So now just a mathematical remark. We have this sequence of states. We start out in a state, we flip maybe a spin, go to the next configuration, go to the next configuration, and so on. And so each of these states I can label as 0, as 1, as 2, as 3. And this sequence of visited states is called a so-called Markov chain. Why is it called a Markov chain? I mean, it's obvious why it's a chain, but why is it a Markov chain? Well, because these transition probabilities only depend on what is the present state and maybe what's the state you want to go to. It does not have any memory. It does not depend on which states you visited sometime in the past. So this is a random process without memory, and therefore it's called a Markov chain. Okay, so this will become important. So now we can go back to machine learning, and remember our goal was to have a way to generate, say, neuron values that follow a desired probability distribution. And so I will now introduce to you a very famous model. It's called the restricted Boltzmann machine. It will become clear why it's Boltzmann, and it will also become clear why it's restricted. Okay. So now it is really laid out in a way similar to neural networks. In fact, you could say it is a neural network. So there are these circles represent neurons, you could say, or units. And likewise for these circles up here. In contrast to the neural networks that we have been discussing so far, the value of these units will be discrete. It can only be 0 or 1, just like a spin or like a bit. So it will not have a continuous value between 0 or 1, but it will be discrete. Also, there will be connections, and I will define in a moment what these connections mean, but they have a similar meaning as in a normal neural network. And then there's a distinction. These blue units, they will be called the visible units, and we call them V. And these yellow units, or neurons, they will be called the hidden units. Let's call them H. Okay, so now I need to tell you what are the rules of this game and really how are we going about this. Instead, so usually for a neural network we will talk about cost functions and so on, but now we are more in the realm of statistical physics, and so we will talk about energies. In the end, I will present to you a process whereby which all these units are assigned random values, like these random spin configurations, but they are not completely random. They are rather distributed according to a Boltzmann distribution, and this Boltzmann distribution has a certain energy. So that's why I will now talk about an energy function. So the temperature really has no meaning in this setting. So when we will compare to a Boltzmann distribution, we will always nominally set kBt equals 1, so that this factor doesn't appear anymore. If kBt were different, I would just need to rescale my energy. That's not a problem. Okay, now how does this energy look like? For a moment, imagine this is a spin model. Spins that are connected by one of these lines, they feel an interaction. Also, each spin feels a magnetic field. How would I write down the energy? Well, first of all, let's look at the magnetic fields. The energy of a spin in a magnetic field is something like the spin variable multiplied by the magnetic field. That's what you know as the Zeeman energy, magnetic field times magnetic moment. And so this is shown here. For example, you sum over all visible units, you multiply this Vi, the visible unit number I variable, you multiply with some arbitrary constant Ai that takes the role of a magnetic field strength. And in this case, the magnetic field is even dependent on the position. So this A also comes with a subscript I. So each spin can feel a different magnetic field. Okay? And the same for all the hidden units. Also, they feel different magnetic fields. They will be called little bj. And then finally, there will be the couplings. So in a typical spin model, the coupling energy and the interaction energy is written like a product of the two spin variables. If two spins are coupled, then you write something like S1 times S2. And the same happens here, only that now my spin variables have different names. Vi, a visible unit, times Hj, a hidden unit. And then there may be a coupling strength that also depends on which units I'm talking about. So Wij. Now it's already interesting that these couplings are called weights because they will play a role similar to the weights we've been talking about in the neural networks. But for now, this is just a spin model with magnetic field and couplings. And then you could try out different spin configurations for both the visible and hidden units, and each such overall spin configuration would have a certain energy, and then when we are talking about Boltzmann distribution in a moment, the lower energies will be more probable. And in the very end, of course, our goal will be that the probability distribution matches some desired probability distribution, because remember, that was our real goal. Okay. But for now, let's just write down these probabilities. So according to if we adopt the Boltzmann distribution, then the probability to find all these spins in a certain configuration, so the visible units are denoted by this vector v, and the state of the hidden units is denoted by this vector h. So the probability to find all of them in a given state is this Boltzmann factor divided by z, and z is the partition function, which is just the sum of the Boltzmann factors over all possibilities. Yeah? So that's exactly the same as for the Boltzmann distribution. I now just explicitly wrote both the v and the h, or if I wanted to be even more explicit, I would write down energy as a function of v1, v2, v3, h1, h2, and so on. Yeah? So the energy is simply, as usual, a function of all the spins. But now we will concentrate on the probability distribution only of the visible units. So I will ask, okay, a given configuration of the visible units, how likely is that? And I don't care what the hidden units are doing. So whenever I say in this probability context that I don't care what these other random variables are, it means I have to sum over all possible values of these other random variables. So that happens in this lower line. So the probability to observe a given configuration V of the visible units is obtained from these more complete probabilities that depend on both V and H by summing over all possible configurations H, because I simply don't care what value the configuration H has. That's similar if I have a Maxwell-Boltzmann distribution, and it's, or if I have a probability distribution for a particle in a given potential, classically speaking, it depends on both x and p, on the position and the momentum, but maybe I'm not interested in the momentum, and so I will integrate over the momentum and only obtain a probability distribution over position. Okay. And so now I can very precisely specify what is our goal. Let's assume we have a probability distribution that I call P0 of V. And this will not even be specified analytically. It's not that you write it down, but it is only indirectly specified by the set of all training examples. Some training examples occur more often, some occur less often, and that specifies P0 of V. And now I want to adapt this so-called Boltzmann machine. I want to adapt the weights and the biases, or the couplings and the magnetic fields, such that the probability distribution P of V approximates my desired probability distribution. Yeah? So that will be the goal. It's a little bit similar to what we do for neural networks. There also we have all these weights and biases. We change them until the input to output mapping approximates a desired deterministic function. Here it's a little bit different. Here we want to have that the probability distribution, the Boltzmann probability distribution for these visible units approximates an observed probability distribution. Okay. And you can imagine that this is a very important task if we are dealing with big data sets. We look at a data set and we try to at least construct an approximate device that can reproduce this probability distribution. Okay. So are there questions at this point already? So let me go on then. Now, why do we have these hidden units available? The reason we have these hidden units available, or the thinking behind them, the intuition, is that they will somehow control what you see in the visible units. So maybe if one of the hidden units is switched on, it means if the visible units represent an image, that they should represent a dog. If another hidden unit is switched on, maybe it should represent a cat. In reality, of course, you need more hidden units because you want to represent different types of dogs in different perspectives and so on. But this is basically the thinking. So the hidden units are something like a higher level representation of what you will see in the visible units. And now I can also tell you why this is called a restricted Boltzmann machine. You see that there are connections only between the hidden units and the visible units. There are never connections between, say, 2 units of the visible units or between 2 hidden units. So only between those different layers, but not within a given layer, there are connections. And that's actually, that will become very important because otherwise it would be super hard to do anything about this. Otherwise it would be super hard to evaluate it. Okay. So now, I want to have a way to produce samples according to this Boltzmann distribution. And we know already how to do this in principle. Yeah? We do something like the Metropolis algorithm. We do a Markov process whose transition probabilities are just arranged in the right way so that it will give me in the long-term limit the correct Boltzmann distribution. And so we will do something very similar. It's only modified a little bit because there will be an extra trick that we always jump between the visible units and the hidden units, always back and forth. And let me just explain it, and then you will see that it also works to give us the correct long-term distribution. So, if I want to produce a Markov chain, I have to tell you what are the transition probabilities. So I will now tell you what is the transition probability to go from a certain visible configuration to a certain hidden configuration. So what's the probability to go from V to H? And I will define this to be, I will demand this to be the probability of H given V. That's a conditional probability. So when you give me a joint probability distribution of V and H, or of any 2 random variables, I can start calculating conditional probabilities. How do I do that? Well, I take the joint probability, that's the probability to observe a configuration that has both the value V and the value H. And I divide this by the probability of what I condition on. That's simply an elementary rule of probabilities. So this is how a conditional probability is defined. Okay, so let me just take this as a definition of my transition probability. I want it to be the conditional probability. And then if I go back from H to V, I do the same thing, only in reverse. I now take the conditional probability of V given H. And that's almost the same expression you see, but now you divide by P of H. Okay. So this at the moment is just a construction. And now there's a nice thing about this construction. You see, if I now calculate this ratio that we have been talking about, that is the ratio of the transition probabilities from one state to the other and back from the other state to the given state. So in this case, from V to H and H to V, if I calculate this ratio and I insert these formulas here, then the joint probability drops out because it occurs in both. And I only get the ratio of P of H versus P of V. Yeah? And that's very nice. Because according to what I said before about detailed balance, this helps us realize that if I just go on for long enough with this Markov chain, I will arrive at a steady state distribution that is given by the probabilities P of V for the visible units and P of H for the hidden units. And remember, these are the marginal distributions, so-called marginal distributions, which just means these are the distributions that I get if I sum over the other variable. So, for example, sum over H. This is what I get. And so that's very nice now, because it is this P of V that I want to be equal to my desired observed probability distribution. And apparently this Markov chain will sample eventually in steady state, it will sample from P of V. Okay. So it's a slight modification of the usual scheme, simply because I have these two classes of configurations. Okay. So now I want to get a handle on these probabilities. Now I really want to calculate these transition probabilities, yeah? I just want to follow the definitions that I've written down here, also to just make it concrete and to show you that it's actually not difficult to take these, to calculate these transition probabilities. Okay. So for example, what is the probability to observe a certain visible configuration V? It's, well, it's 1 over Z times this sum over all H and then the Boltzmann factor. The Z, for convenience, I bring to the other side, so I don't have to carry it along. But so now I need to evaluate this. So here I still have the Boltzmann factor that appears in the joint probability to observe both V and H, but eventually I want to sum over all hidden units. So I can just insert the energy expression that is shown up here with the couplings and the magnetic field terms. But I still have to sum over H, which seems a non-trivial task, yeah? Because there are many hidden units, and to sum over all configurations, that in principle requires exponentially many configurations, yes? Because each hidden unit can be 0 or 1. If there are n of them, then there will be 2 to the n of such configurations. So it seems like this is a really big sum to carry out. Now, there's several good features about this, you see. You see that the hidden variables, the hidden units, only occur linearly. So it's hj here, hj there. There's never a quadratic term. That will be very helpful. Also, you see, when I have sums in an exponent, I can decompose this into a product of exponentials. Yeah, e to the x times e to the y equals e to the x plus y. So that means for each of these terms in these sums, I can actually write this term individually and then make a product over all the individual factors. So this is something that I show here, product over the individual factors. And then I remember that the sum over all configurations H in principle is a sum over the value of H0, a sum over the possible values of H1, sum over the possible values of H2, and so on. This, of course, exponentially many, if I really do all these summations, these are exponentially many terms still that I sum up, yeah? But in principle, conceptually, to write down the sum is not so difficult. And now I will combine these two observations, that is, this can be written as a product, and this can be written as a multiple sum. Because you see, the nice thing is, let's, for example, just look at this particular term. I will have one factor in my product that, let's look at j equals 3 just for a moment. There will be one factor that reads like e to the b3 times h3. Yeah? And now I want to sum over the h's, but this term only contains h3, so I only need to look at the sum over h3. And the sum only is a sum over two possibilities, 0 and 1. Yeah? So that is actually very easy to do. Now, I have to be a little bit more precise. The h3 will also occur in one of these terms, so I will pull both of these terms together. But again, it's a sum over h3 having the two possible values, 0 or 1. And that is exactly what I've written down here. The 1 comes about if I set hj, h3 in our example equal to 0, because then the exponent is 0, e to the 0 is 1. And the second term comes about when I set h3 equals 1, because then it just multiplies the bj and these other terms, and it gives rise to this expression, which I abbreviated as zj. And so this will happen for j equals 3, but it will also happen for all the other terms, and in the end I just end up with this product. Yeah? So what seemed very, very complicated in the beginning, I can actually do analytically by hand. Yeah? Again, by noticing that the E of a sum is the product, and that the sum over all configurations is a repeated sum, and that each of these individual sums will only be responsible, will only act non-trivially on one of these factors. Okay. So if you don't believe it immediately, you can, for example, go through it yourself. For example, keeping only 2 of these terms, H1 and H2, then you will see that this works. So I have been able to calculate this analytically, which is very good. So the P of V is now given as this product. I mean, it's still a product of multiple terms, but it's a product. And now I can go one step further. I can say, if this is P of V, then what is P of H given V, this conditional probability that I need for my transition rate? Well, according to definition, it's basically the joint probability of V and H, that is essentially the Boltzmann factor, divided by P of V, which we just calculated. Now I can just insert the energy expression once again, and I can insert the P of V expression that we had calculated, and I will find that it is this product over all j, by which I number my different hidden units, e to the zj times hj divided by 1 plus e to the zj. Remember that zj itself contains the visible unit values, so this is why this conditional probability doesn't depend on the visible unit values. And it also, of course, depends on which particular hidden unit configuration we are talking about, because these occur here. Okay, so now what does this mean? If this probability, that will become my transition probability, is a product over all j, well, you know, whenever a probability distribution is a product, that just means that these are independent random variables. Yeah? So I have the probability of A and B is probability of A times probability of B, means they are independent. What does it mean for us? Well, for us it means that all the different Hj that are belonging to the different factors, they are independent. So when I make these transitions from V to H, it's not that I have to somehow, for each possible configuration, for each of these exponentially many possible H configurations, calculate these probabilities. No, I can independently say I update, I make a transition probability for H1, for H2, for H3, because they enter as this product. Yeah? So all the Hj are independently distributed when I take the step going from V to H. And their probabilities are essentially written down here. So the probability of Hj equals 1 given V equals, well, it's the term for this particular j when I set Hj equals 1. And you read it down here. But now you recognize this term. We've seen this before. It's actually the sigmoid function. This was one of those nonlinear activation functions. Yeah? So it's a sigmoid function as a function of Zj. And the probability for Hj to be 0, well, I just need to insert Hj equals 0 here. It's 1 divided by 1 plus something. And, well, as you expect, it's just 1 minus what we just calculated. It must be 1 minus because Hj only has these two possibilities. And if the conditional probability of it being 1 is this one, then the conditional probability of it being 0 must be 1 minus this. Of course, they add up to 1. Okay. So now what seemed very complicated has become very simple. If I want to do one step of this Markov chain, that is going from a given visible configuration to a new hidden configuration, I don't need to treat the hidden configuration as a full configuration. I can update individually each of the hidden units according to these probabilities. So to summarize, give me some visible unit state vector V, calculate these Zj according to the rule that was written down here. The couplings will enter, the visible units will enter, the magnetic fields will enter. And then just calculate this simple sigmoid function, and that will tell you the probability with which hj should be set equal to 1. And then you just assign 1 or 0 based on this probability. And then you get a new configuration, a hidden configuration. It may be a string like 1, 0, 1, 1, 0, 1, calculated according to these probabilities. You throw dice at this point. Okay, and that's it. That's basically the whole concept. And this is a step that only works because we have this restricted Boltzmann machine where there are only connections between hidden and visible units. If we had had something more complicated, if in this energy function not only do we multiply v and h, but also h and v and v, then this whole thing would break down. It wouldn't work like this. Yeah. Okay. And then this was only one part of the Markov chain, going from visible to hidden units. We also have to go back from hidden to visible units, but this is basically the same calculation, only in reverse. And you would do a similar thing, only here the different A, the magnetic fields, enter the other magnetic fields, and here the Z depends on H now instead of V, and we're talking about V given H, so it's all just reversing the roles of V and H. Okay. So now that's great. So in principle now, what have we gained so far? Well, we have found a very efficient way, Monte Carlo way, to sample from this Boltzmann distribution, which is determined by the energies, and the energies are determined by these magnetic fields A and B and by the weights W. Okay. So if you give me any such Boltzmann distribution, any energy of this sort, I can very efficiently give you the sample using Monte Carlo. But this is, of course, only half of the story. What we really wanted is not an arbitrary Boltzmann distribution, but we wanted to adapt the energies so that we get exactly a desired distribution. P0, we called it, P0 of V. So how do we do this? P of V should be as close as possible to P0. Well, we already discussed such a situation before. If we have two probability distribution and we want to have a measure of how close they are, we already know a kind of cost function that tells us, namely it's the categorical cross entropy. So it looks like the entropy. So here you would have one probability distribution, P of V, here another probability distribution, P0 of V, and this would be the cost function. And by minimizing this, we will try to match P of V to P0. So you could view this whole thing as a function also of these parameters, W and A and B, and you want to change these parameters so as to minimize this cost function. Now, there's a tiny little problem here. In all the earlier examples when we were dealing with this categorical cross entropy, the V usually just ranged over the outputs of a neural network, and there were only a very few values, like 7 output neurons, let's say, and then we can actually explicitly carry out the sum. But this is no longer possible here. Here we have exponentially many configurations V. Each V is one visible configuration, and so we cannot possibly carry out this sum. So eventually, of course, we will have to resort somehow to the Monte Carlo, and that's why we prepared ourselves by talking about the Monte Carlo now. But for the moment, let's not worry about this. Let's just pretend that we could calculate this sum, and let's just take the gradient of C with respect to the parameters that sit in the energy. So this is the usual ansatz, yeah? So for a moment, we forget that it's complicated. We just do brute force analytical calculation, and then we hope that we end up with something that we can interpret, and which is actually not so difficult in the end. Yeah. Okay, so for the moment, let's just take the gradient of C. And remember, these parameters that I'm talking about, they sit in the P of V. The P0 is given externally. That has no parameters. Okay, so I don't know whether I want to go through all the details, but this is a type of calculation that probably you have already seen in statistical physics if you have seen statistical physics classes, yeah? Because it's the typical, say, derivatives of a partition function or of a free energy, actually. Yeah? So this is our cost function. I want to take the derivative, for example, with respect to these weights. These only enter this second term, the logarithm of P of V, so I only concentrate there. Then, since I take the logarithmic derivative, I get 1 over whatever is the argument of the derivative, the argument of the logarithm, and here it's the derivative in the numerator. And then I already expressed P of V in terms of the sum over h of P of V comma h. Yeah, so this is how P of V is defined. Okay, now I have to do this derivative. I know that these joint probabilities, they look like the Boltzmann factor, but divided by z. That's important. For normalization, there's this division by the partition function. So if I take this derivative, there will be now 2 parts. The derivative will act on the Boltzmann factor. That's nice. But also there will be another part where the derivative acts on the 1 over the partition function. Yeah? So, and we should not forget either of them. They are both important. Okay. So now this is how you carry out the derivative in principle. And now if you really apply the derivative to this exponential, you get basically the derivative of the energy times the exponential. And in the energy, the Wij is multiplied by Vihj. This was how the energy was defined. Just to flip back here. Here, Wij just sits next to Vihj. So if I take the derivative with respect to W, all I'm left with is this product of Vi and Hj. So this happens here for the first term. And then for the second term, actually, if I express my z again in terms of the sum and again in terms of the Boltzmann factors, you will find a very similar looking expression. Okay. So now I can summarize whatever I have learned. Let me go back to the cost function. I took this derivative. I ended up with these terms. I will now combine this with the P0 of V and the sum over V. And then let's look at what happens. So what is sitting here in the denominator is essentially, since I'm summing over h, the P of V, modulo the 1 over z. Yeah? But the 1 over z is also missing in the numerator, so I can expand both the numerator and the denominator. And so I claim this first term, when you insert it here, just gives this. So Vihj from here times the conditional probability of h given V times P0 of V. So the P0 comes from up here. And the other term, if you look at it closely, actually is just a sum over V prime H prime, and then this product again, P of V prime comma H prime. I could also, if I wanted to, I could rewrite this second part. Let me see whether I did this actually. Yes, yeah. So this is the same equation, only I rewrote the second part. Instead of the joint probability of H prime and V prime, I write it in a way that's more similar to the first part. P of H prime given V prime times P of V prime. Okay? So, after a long calculation, we finally arrived here. The question is, what does it mean? Can we interpret it? Yes, in principle, we can interpret it. So, how would I evaluate this first sum if I wanted to evaluate it stochastically? Yeah? Well, you see P0 of V appearing. So maybe that just means I should draw a visible configuration according to P0. But what does it mean according to P0? Well, P0 is the probability distribution of training samples. So you are giving me the training samples, and that means sampling from P0. Yeah? So I just pick one of the V that someone gives me from the observations, and that is already, if I then were to average eventually over V, I would exactly do this thing that I sum over P0 of V. Okay, but then that's not enough. I should still take a step, namely from this V to H, according to the conditional probability, which, remember, was our transition probability. And then I should take the V that someone provided to me and the H that I just randomly sampled according to this step. I should multiply their values, and that's it. And then I should do the sampling many, many times that I effectively get the sum over both V and H. So it's a little bit lengthy explanation, but this is really how we could evaluate this first term. So again, you just draw a random V from the training distribution, P0. You make the step from V to H. You take this product, and then you do it many, many, many times. You take the average. This is what will result. So this is actually not very difficult to get this first term. Even if you don't have explicit access to P0, you just sample from P0. What is much more difficult is the second term. It almost looks the same, but unfortunately, instead of P0, I have P of V. Now, in principle, we know, of course, how to sample from P of V, because we said we can construct this nice Markov chain I told you before. But at least we would have to do this. Yeah? I would have to go through the full Markov chain. Okay. So, just to remind you, because you can easily lose track. So, we are trying to minimize this cost function in order to make P match as closely as possible P0 by adapting the weights. We have calculated the gradient of the cost function because that's what we would need in gradient descent. We saw that this gradient can be expressed by these terms, one of which can easily be sampled stochastically, and the other is a little bit harder because it involves this P of V, which is the steady state Boltzmann distribution of my Boltzmann machine. Okay. So, and now here comes the final trick. So, this first term, as I said, I can interpret as saying, take an arbitrary training example, take one step from V to H according to this conditional probability, and we know that this step can be taken very easily. All the individual hidden units can be sampled independently from each other. This was this product of probabilities. And then that's it, and calculate V times H and do this many, many times, and you will get an estimate. The second thing, in order to even go to the steady state distribution of V, I would need to go through this Markov chain maybe many, many times, 100 steps, and then finally I would arrive at a distribution, stochastic distribution of the V's that mimics the P of V. But there's an approximation that people like to take. Instead of going through the full chain, they just take one more step going from H to V prime, and then maybe going from V prime to H prime, and then they leave it at that. This will only be an approximation, but as I will show you in a moment, when you're already close to the good solution, this is a very good approximation. So this is why it works. And so then, how would we then finally take the update of my weights? Well, that's shown here. So delta of the weight, Wij, is exactly some learning rate times the gradient that we just calculated. And the gradient that we just calculated is essentially this V times H averaged according to this prescription, minus the V prime H prime averaged according to this prescription. Yeah? So this is what people do. So it's a little bit mathematical, but I at least wanted to go through one of these more advanced examples. This algorithm is called contrastive divergence. Contrastive, well, obviously you take these samples and you contrast them with the other samples and you take the difference between them. So now I want to prove to you that at least when P0 equals P, when we are already there, then this hopefully is a fixed point of this update equation. Otherwise, we're doing something wrong. Yeah? At least this should be true. But, well, that is pretty simple to show, because if P0 equals P, then, the distribution of this V is the same as the distribution of this V is the same as the distribution of this V, because we are already in steady state. It's all the same distribution. It's all P of V. So then the V prime is no different than V, and so to speak, the second term exactly cancels the first term. This we could also see a little bit earlier, of course. If this P of V equals the P0 of V, then these two terms are exactly equal, and it cancels, and nothing changes anymore. Okay. And so, by this rather long route, we have finally arrived at a prescription how to change our parameters in order to mimic, as close as possible, this distribution that's defined by the training samples. I only talked about the W, the weights, but of course there are also the magnetic fields, and you go through the same steps and you find very similar looking expressions down here. Yeah. So this is what's called a restricted Boltzmann machine, and what we just discussed means training the restricted Boltzmann machine. So it really means you give me a lot of samples, I do this little trick of taking the sample, doing a few steps of this Markov chain. In the Markov chain, of course, in order to do these steps of the Markov chain, we have to evaluate these probabilities, but it's simple because all the hidden units are updated independently. And in these probabilities already the weights and the biases will occur. So that means, yeah, it will depend on these weights and biases, but I'm also changing them during the training. So this is what happens. Okay. And so now this is a way to mimic known distributions. And I want to show at least one example, which is very nice. So remember, in the very early days of this lecture, we looked at handwritten digit recognition. So there's lots of images, and you can do supervised learning. You know that this handwritten 5 is really a 5, and so on. But you can also use these images for other purposes, of course. And especially you can just say, let me completely forget about the labels. Let me just take this as a large data set of images. I draw a random one of these images, and this is my training sample. And then I want to mimic the distribution. I want to create a Boltzmann machine that will be able to mimic the distribution of these images. So not only will it be able to mimic whether the 3 and the 5 occur with 20% and 50% probabilities, but in particular it will also be able to generate on its own in the visible units proper pictures of handwritten images, because that's what it sees. You train it on handwritten digit images, so it will produce for you random handwritten digit images. And so that is what is shown here. So for example, so each of these images here, I don't know how many pixels it has, 20 by 20, let's say, represents the visible units. So maybe there are, in this case, I don't know, 400 visible units. So black and white. And this obviously represents a 7, I would say. Now this is one configuration of the visible units. Now you take your Markov chain. You take this to the hidden units, which are not displayed here. You go back to the visible units, which would be another such picture. You do this many, many times. Maybe you do it 1,000 times, just for fun. And after 1,000 steps in this Markov chain, you arrive at this picture. It's almost the same. Only a few pixels have changed a little. Yeah? And then you do this again, another 1,000 steps, another 1,000 steps, another 1,000 steps. And oops, something is happening a little bit. And oh, you have changed the category of the image. It has become a 9. So by doing this Markov chain, most of the time you stayed in the 7, and then at some point there was a flip, and it went to a 9, basically. And then if you go on, you go to a 5, and so on. And it will really cycle through a lot of random images, but most of them are recognizable as handwritten digits, because that's what it has been trained on. And so that's the same is true for each of these columns. So for example, I don't know, you start, let's say, many of them are very stable, but for example, here you start with a 9, and then suddenly you switch to a 6, and you remain with a 6, and so on. Yeah, so these are really the Markov chains of this Boltzmann machine that has already been trained on all these handwritten digits. And of course, you can do this for more complicated images. These are just simple examples. And so, well, I don't know how meaningful this is, but people try to look, of course, inside, want to understand what's going on. And in this case, there were 100 hidden units. And so each of these hidden units is, of course, in principle connected to all of the pixels, to all of the visible units. And so that means there are now 100 such pictures. If I draw the weights, then each of these 100 hidden units is connected to all visible unit pixels, and I can draw these weights as a grayscale picture. So these are, for example, this is a picture of the weights for this particular hidden unit, as it is connected to all the visible units that represent the pixels of this picture. And, well, you cannot see very much, but you can see that there are somehow features that you recognize for the handwritten digits. They are also encoded in these weights. Okay. Okay, good. Then maybe I finish today by telling you a little bit about how people extended these restricted Boltzmann machines. So the first thing you can do is the following, and that follows a little bit the game that we already played for the autoencoder. You remember autoencoder just tries to turn the input image to the output image. So basically just encode it very efficiently in some bottleneck and then give it back in the end. But then we said just chop off the decoder part of the autoencoder and replace it with another small neural network in order to be trained in a supervised training task, yeah, because it has already well approximated some important features, and then you can do supervised training on top of this. And the same you can try with a restricted Boltzmann machine. So here you have the visible units, here you have the hidden units, and instead of just always cycling between visible and hidden and back and forth again, which we needed for the training, you say, now I have trained it, and my hidden units somehow represent something important, apparently, about my typical visible unit configurations. And so now I take the values of the hidden units and I feed them in another step onto an output layer that could solve a classification task. And I do supervised training on this. In the supervised training, I will only adapt these connections, and I will leave untouched those connections because I have already trained them before. So concept is very similar to what we did with the autoencoder. So first you train the restricted Boltzmann machine without providing any labels, and then you want to have a certain type of label, so you add this little extra layer on top, and you do supervised learning. So you can imagine why this is important. So the training on such a large data set of images may be a little bit expensive. So maybe you want to do it on a supercomputer or something, on a cluster. But then, who knows, maybe the labels will be provided by the end user. And one user wants to have this kind of labels for the pictures, the other user different kinds of labels. And then that could be efficiently done because you only need this extra training task. Okay. Then there's another thing. Maybe you want to make your restricted Boltzmann machine more powerful. We know already from supervised training to make networks more powerful, we just need more layers. So you can play the same game here. So, for example, you can do this. First, you do training on this simple restricted Boltzmann machine with one visible layer and one hidden layer. Then you fix those connections, but then you add another hidden layer and treat this, these hidden units H1, you treat them as if they were visible units for this second restricted Boltzmann machine. Yeah, because if I sample from my actual training samples for these visible units, then and then I do one step from visible to hidden, I also get some sample of these hidden units, which I then can interpret as a new visible unit sample for the second Boltzmann machine. And so on. I can go on and build a stack of different hidden units. Now, the good thing about this was that I have trained these weights, then I freeze them. I train those weights, then I freeze them. Then I train those weights and I freeze them. So I can build many stacks without too much numerical effort. And then I could say, oh, now I have built this multi-layered restricted Boltzmann machine. Now I can maybe relax this assumption that I freeze the weights, and I can still fine-tune them by training all of them. So either as a restricted Boltzmann machine or, for example, by supervised learning, maybe there's a last layer which really gives me labels. And so, yeah, this was also one of the first examples of deep neural networks. So now I just want to briefly mention how this is applied in modern quantum physics. So this will be even more advanced at this stage, but maybe you're interested at least in the fact that it can be done. So in quantum physics, usually we cannot solve problems exactly, especially if it comes to quantum many-body physics. For example, if I have a spin model in quantum mechanics, the Hilbert space grows exponentially. I would have to diagonalize an exponentially large matrix to get the ground state. This is very difficult. So what people often do is they make a variational ansatz for the ground state wave function. They just parameterize their ground state wave function with a few parameters. They calculate the energy expectation value. They say, oh, let me change these parameters so that the energy expectation value is as small as possible. And then that's at least an approximation for the ground state wave function. And of course, over the years, people have invented many different variational ansatz wave functions. Now, these people here were inspired by restricted Boltzmann machines to invent a new variational ansatz for wave functions. And so it works like this. So if you have a, say, spin system with n spins, to represent its wave function means you have to assign a wave amplitude, psi, to each possible configuration. There are exponentially many configurations. Each of them represents a basis state in the Hilbert space. Each of them, therefore, has a psi, a wave function amplitude. And that describes only a single wave function, maybe the ground state wave function. So listing these 2 to the n in general complex numbers only defines a single wave function. And the question is now, how can you make a good variational ansatz for this single wave function? Well, and not surprisingly, the ansatz here is very, very closely related to the restricted Boltzmann machine. Actually, it's identical to the restricted Boltzmann machine. So it's like our expression for the P of V. Yeah? So you sum over H, E to the, and then there are these terms. You recognize everything except the sigma Z of J are the values of this particular spin configuration for which you want to evaluate the wave function amplitude. So these represent the visible units, essentially. Now, since wave functions can be complex, in principle, also these W and B and H and A in the most general case might have to be complex. But let's stay with a simple case where they are not complex. And so now, this is only an ansatz, of course. We don't yet know how to choose these weights. We don't, the situation is now a little bit different, right? We don't want to mimic a given distribution that is given by training examples, although people also have used it for that purpose in the meantime, by experimental observations of many body states. But rather, here we want to minimize the energy because it's a variational ansatz to get the ground state. So we have to calculate this energy expectation value. The question is how to calculate this. And there's a little catch here, because what we are given is only psi of s. That's the amplitude, the probability amplitude psi for a given configuration S. In order to calculate this expectation value, or even just this norm, you have to, in principle, sum over all exponentially many different configurations. And again, it's the same problem as before. If you were able to do this easily, then you probably wouldn't need these techniques. So what they did on top of this variational ansatz that is coming from a restricted Boltzmann machine, what they did on top is another Monte Carlo approach to sample from the wave function. Again, this is known in the field to do some quantum Monte Carlo to try to sample from a wave function that is given and to calculate such expectation values like the one shown here. So there are a little bit extra steps involved, but the basic step is that you have this ansatz that is motivated by the restricted Boltzmann machine. And then, of course, after that, after you can evaluate this energy expectation value, then it's clear what is the goal. You just now want to change the parameters, the weights and the biases in this ansatz in order to minimize this energy, because that is the approximation to the ground state. Okay. And so they were able to show that at least for certain models, this actually provides very nice results. I don't go into this graphical depiction of the weights, but here you see the error of the energy that they got out, and this is some measure of how many neurons they kept, so to speak. And you see that the error keeps decreasing as they add neurons, as they keep adding hidden neurons, and they are better than certain other variational ansatzes. So this is a very nice application to physics. It's a little bit involved, but it involves this restricted Boltzmann machine. Okay, any questions about this? Yeah? In general, they could be complex numbers. In the simplest cases, they are still real numbers. But in principle, yes, they can be complex numbers because psi has to be a complex number. Okay. Okay, so then there will be a tutorial next Wednesday, and then I'm back in the week after that. Okay, thank you.